Pablo Miranda Carranza is a senior lecturer in architecture at Lund University. For the last 20 years, he has been looking at what happens to architecture when it is programmed rather than drawn. In the process, he has built interactive installations, written generative design software, and published academic essays and articles. His current academic research examines how software and programs have historically affected the way architecture is made and thought. To look at code as a historical material implies to expand traditional historiographical methods to include the rewriting and execution of programs and algorithms. Miranda Carranza is at present working on a project that examines the history of software in urban planning and the apparent incontestability of the results in governance and decision-making. The research is supported by a grant from Vetenskapsrådet, the Swedish Research Council. Pablo Miranda Carranza obtained his PhD from KTH in Stockholm in 2018 and was a postdoctoral fellow at the History, Theory and Criticism program at the Department of Architecture at MIT in Cambridge, Massachusetts during 2022. Welcome.
I'm going to talk about HIDECS2, Artificial Intelligence and Architecture in 1962. The reason to look at something, at something that happened in 1962, it's because our narrative of progress, in our narrative of progress, everything needs to appear new. And we often reject any link of current technical conditions with the past. In the best case, we refer to this past as something we have discarded, a failed condition that we have finally improved on and which we can leave behind in our continuous push towards an always better future. Artificial intelligence is an example of this, even as we discuss in this conference its relevance for architecture. Despite all claims of novelty, artificial intelligence was one of the first fields that influenced the discipline of architecture during its early interactions with the technologies of the computer. In his PhD, the first ever awarded in the subject of architecture at Harvard and published in 1964 as Notes on the Synthesis of Form, Christopher Alexander proposed to use AI in design. Much of the work presented in the notes in his book was based on Alexander's collaboration with MIT's Marvin Mannheim in the HIDECS2 program, also used in Alexander's work with Sergei Chermayev, Community and Privacy Towards a New Architecture of Humanism, published in 1963. In this presentation, and as much as its shortness permits, now maybe even shorter, I will attempt to a close reading of HIDECS2, of this program that Alexander wrote, and unpack some of the consequences and principles written in its code. I will use a method to read and interpret programs and code close to what is known as critical code studies. HIDECS2 was written in Fortran, assembly program, or FAP, an assembly language for the IBM 709 and the 7090 that Alexander used for running his code. Most of this code is available as part of MIT research report, which number RS22. I have reconstructed the original code in Python, following the descriptions of the algorithm in the report. And I have made it available in that GitLab link. If anyone is interested, I can give it to them later. And in the process, I have examined the types of techniques used by Alexander, their origin and implications, both technical and ideological. And by ideological, I mean in its widest sense, in terms of the systems of ideas and values in which these techniques participate. I will especially explain how Alexander's code implemented many of political scientist Herbert Simon's ideas, both on artificial intelligence and on the organization and rationalization of intellectual labor. And much of this work I'm presenting, it's part of a paper that it was with the title Making Sense Without Meaning, that was published as part of Utopia Computer, which was began as a conference in Berlin in 2019. In 1956, computer scientist John McCarthy organized the now famous Dartmouth Summer Research Project on artificial intelligence. It was here that the new field dealing with thinking machines was first given the name of artificial intelligence. Herbert Simon was there with Alan Newell and presented their logical theorist program, one of the first uses of AI, and the programming language IPL used to implement it, and which inspired McCarthy, the organizing of the conference, to develop a language called Lisp, which is actually powering this presentation because it's using Emacs, which is written in Lisp. Beside his presence at the Dartmouth workshop and his many contributions to artificial intelligence, operations research, and organization science, Simon's idea of bounded rationality in the fields of economics and decision-making gave him the 1978 Nobel Memorial Prize in Economic Sciences. The basic principle of bounded rationality is the limitations of rational choice, a grounding concept in the classical economics of Adam Smith or David Ricardo. Simon explained this limitation to rational choice as the result of the restricted computational and informational capabilities of individual actors. The limitations is also the basis and reason for HIDECS2, Alexander's program, which was meant to assist architects and designers. If the individual mind was a limited computer, it was easy to argue that the solution to these limitations in the case of design was the use of actual computers of higher processing capacity to augment this process. To make this argument work, it was imperative to present design as a computational task of such complexity that it will necessarily require the use of computers. This was, in fact, the basic idea of Alexander. And he described I'll show you, he described the design process in terms of solving a set of design requirements. For example, this is, hopefully it will work. There. So this is, for example, from publicity and privacy, the requirements that he thought they would need for a sort of suburban home, efficiency parking for owners and visitors, adequate maneuver space, temporary space for service and delivery vehicles. You can get the feeling. Pedestrian access for automobile to dwelling involving minimum possible distance and fatigue. And then after he kind of wrote this list, he sort of like linked each of these requirements to the ones that they were kind of like, that had a relation to. So, 9 is linked to 3, 6, and 8. And if we kind of look at 9, it's stops against crawling and climbing insects, vermin, reptile, birds, mammals. And it's connected to 3 and 6, which is reception point to group, sheltered, delivered, and waiting, provisions for informal information, mail, parcel, and delivery boxes, and the storage of parcel cards, etc. You kind of get a bit the idea. So the design process was a task to begin with of dividing or designing these requirements. He had another famous example that's from the Notes on the Synthesis of Form for an Indian village where he actually lived, and this includes 141 different requirements, like factions refuse to cooperate or agree, price assurance for crops, prevent the spread of human disease by carries, infection, contagion, Harijans regarded as ritually impure, untouchable, etc., proper disposal of dead, rules about house doors not facing south. So he kind of wrote a list and then how these kind of things were related. And it doesn't matter, according to him, if you were designing a village in India, or a propeller for an airplane. Any kind of design sort of problem would be kind of represented through this kind of mechanism. Which, I mean, some people has been, of course, looking at this particular project from a post-colonial perspective and what it meant. So the idea for, and one of the things that happened is that they kind of also produce a graph. I just only show the one for the community and privacy, which is this. They basically a table of all the requirements. They have like the number of the requirement and which other ones they are linked to. You see the 141, it basically doesn't really fit in the screen. So I won't show that. You have to make it very small, everything. So his idea was that that then once that you have like that presented, like that kind of very huge complexity that is completely overwhelming and beyond the capacity of anyone to solve, one would sort of have decomposed, you could have like all the requirements and how they're related to each other. And then you would sort of like divide them into requirements that are closer linked or tightly linked to others. And then you would kind of like decompose the problem into something a bit like this, that it would make it into a tree, and then you would sort of like, you would end up here with problems that are kind of closely related, and you would solve them, and then you would solve all of these. You would start here at the bottom, and then you would sort of like put them together at another stage, and then you would synthesize going from the bottom up, all the design problem, now that the complexity was kind of broken down. And I'll show you now. That's the main demo. Hopefully it's working here. So now it's calculating the sort of doing all the calculations for the solving the 33 assignments of the kind of problems for community and privacy. So the remedy to all these problems of how to solve this complexity was this idea of this program that is now calculating. But this program, it was not just, it was not only the argument of the sort of complexity or the bounded rationality of human mind that Alexander had borrowed from Simon. It was also the solution that he's calculating now in the form of a program, a sequence of operations that could be orderly executed to produce a design. The form of this sequence originated in the analysis of complex organizations such as business, factories, governmental institutions, or military units as part of the book Organizations, written together with James March. In the book, they proposed a factorization of the whole organizational complex into a number of nearly independent parts, so the definition of the situation the organization dealt with would be sufficiently simple to be encompassed by a human mind. According to Simon and March, organizations often display a structure of departmental division that corresponds to the hierarchical subdivision of the problem they deal with, which allows for decisions to be taken at different levels of a hierarchy, rather than dealing with the whole complexity of a decision at once. This is the end of the program calculation. The factorization of design, following Simon's principle, had the advantage of allowing the solution of each of the finals of problems to be produced by separate groups specialized in the specific subtask, making best use of bounded human computational resources. This reduces complexity tasks into small and simple enough units that can be dealt with by limited human cognitive capacities. Alexander's methods to compute this factorization of the requirements was based also on Simon's idea of heuristics, a concept first formulated by the mathematician George Polya and his relation to computers. Simon had outlined this idea of heuristics in a speech at the 12th National Meeting of the Operations Research Society of America in 1957, just a year after the Dartmouth workshop. Heuristics would, according to Simon, address the ill structure problems which made up the majority of top-level management and executive decisions, by handling with appropriate analytic tools situations that until then were tackled with judgment and guess. Through the resultant theory of heuristics, as contrasted to algorithmic problem-solving, intuition, insight, and learning would no longer be exclusive possession of humans, as any large high-speed computer could be programmed to exhibit them also. The study of heuristics will result in a science of intelligence. Their understanding and simulation by digital computers would allow to deal scientifically with ill-structured problems and to make the computer coextensive with the human mind. Alexander HIDECS2 can be seen as a clear exponent and application of such heuristic methods, both in its idea of extending or supplementing a designer's mind, but also technically in its use of a hill climbing algorithm, a very basic type of greedy optimization method to find best subdivisions of a set of design requirements. I can maybe zoom up a little and show how this works. So here we see basically what the algorithm was doing. It's you can see the numbers there are the requirements, and they're sort of divided. It starts with a random subdivision of them, and then it starts moving them one by one to the other side and calculating its value, how it will perform, how well good this division is. So it just keep doing this, and it's trying to kind of get the ones that have a lower value there. So it sort of like keeps on improving and trying, testing until it sort of like finds some kind of like, minimal condition. And then it does that many times to find a sort of a decent solution. And then it kind of like goes when it has like one of those, like in this case, I think that this is 9, 11, 14 is a kind of a good partition. So it kind of like, it just, does that sort of, it takes all the conditions, and it sort of starts dividing them into smaller groups, and then sort of goes more and more into smaller. And at the end, it sort of puts them all together like that. So that's the kind of the program, the instructions the computer would give to a human designer on how to proceed solving a problem. And just to kind of like show a little bit, remind a little bit which ones they were. So these are, so then it says like 16 and 21 should be sort of maybe considered together. What is 16? What does it say? Fire barriers. And 21, control at source of noises generated in the communal domain. It looks like a very absurd design process, but anyway, obviously we don't really design like this, so we don't really use Alexander's method to design in architecture. But despite Alexander's method's eventual demise, and even if he was very influential in design thinking, as an explicit design process, this specialization and factorization of design is easily recognizable in today's structuring and organization of architectural production. Well, a few decades ago, architects' training included the skills required to manage most parts of the design and building process. Today, the ideation and execution of a design corresponds closely to this compartmentation into domains of expertise dealing with the sub-goals of, for example, ventilation, structural calculation, interior design, fire regulation, or people flow and circulation. In a time of both fear or uncritical enthusiasm about AI in architecture, it is worth thinking to what extent the current state of affairs And the position of the architect is the result of the early AI used by Alexander. Its effects may not have been direct, but the arguments and solutions behind it may be recognizable in today's practice. After all, the factorization of the architectural design process has followed a similar argumentation, posing that the architectural design process is increasingly complex and beyond the bounded cognitive capacities of traditional architects, and thus factorization and division of labor, often achieved through the use of digital systems like BIM, for example, nowadays, a necessity. Looking back to this early example of AI in architecture, the idea then is not so much how technologies such as AI may affect us directly, but how it operates in us ideologically, how these technologies dovetail with larger political and economic forces by being their result, their representations, and by executing their programs. I think that's it.